let's go ahead and get started. I apologize, my video is having issues on the stream. There we go. All right, so before we dive into stoichiometry, are there any questions about anything? So we're almost like done with the quarter, so that's kind of scary. So, right, this is week 8 that we're just ending. And so, right, next week is obviously week 9 and also Thanksgiving. And so, if you've looked ahead at the syllabus, I've seen, right, we have no lab next week, right? So, I just obviously don't want to have a Tuesday section. Obviously, we're not going to have a Thursday one because you'll be too busy eating or whatever and not being at school. But Tuesday would be a good time to do makeups if you need to do anything. And so that could be anything from labs to if you're missing quizzes or anything. So, right, that's a good time slot to make stuff up. Or just if you want to, come by, chat about anything, that would also be a good time. So I'll kind of put that as office hours as well. So just put that on your radar.
And that Tuesday would be in the lab room where we would be able to find you?
Yeah.
Okay.
Yep, so I'll be there. So, yeah, 3:12 so that we could do lab makeups if that needs to happen. And then, so the other thing is so I've kind of been slacking a little. This quarter flew by. And so I was supposed to post some sort of journal article summary assignment, and I've kind of slacked on that. So I decided to kind of still give it to y'all, but instead of being a full assignment, it will be 5 points bonus on the final, because, right, we won't have opportunities for corrections on the final, so that will help kind of buffer people's grades. And so I'll post the assignment, and I'll kind of go over it, though. And so this is from last year, so I think I'm going to fix it a little and make it shorter. And so basically, the idea is that in winter and spring quarter, we'll do some sort of research paper. And so the idea is winter, you would kind of make a draft of this paper, and then over spring break, I get to read them. And then in spring, you do the final paper and then some sort of presentation on that topic. And so for the assignment, it's just kind of to practice writing an abstract. And so I'll probably change this because last year I had them do 1 to 2 paragraphs. I'll probably cut this down to a 1 paragraph, like 5-sentence abstract summary. And so the idea is, right, just take a paper, and I know it could be overwhelming. So if you just want to use a paper that we've seen before, that would be appropriate. So all the ones from our JChem Ed. And so all we want to do is, can we summarize it? And so I just put a bunch of other topics, so, right, you don't have to be married to anything that we did in lab. So if you're interested in, whatever, solar technology, drug development. So these were popular topics last year. People like antidepressants and nootropics. I've just put under there like agriculture production. And again, right, the sky's the limit. So whatever you're interested in. And so all I care about is, again, you write a little abstract. And so every JChem article, though, that we've looked at, then you can see, right, that they include an abstract, so you can kind of read that to help you. And if you do choose a JChem article, right, you can, of course, reference that abstract, but, write your own, but you kind of have an idea of what they're looking for. And so I'll show another example. And so this is a little wordy. And so this is from this guy, Derek Lowe. He's an organic chemist in the pharma industry. So he often writes a lot of blogs. But this is a nice summary. Obviously, it's a lot longer than what I'm asking for, but at least kind of gives you an idea. And so here's, the paper, blah, blah, blah. So, right, it's a very dense paper. So you can, yeah. All right, so this is like a full organic chemistry paper. It goes through all these synthesis, but then, right, the idea is he's just trying to summarize what they talked about. So they were talking about flipping tertiary centers, and you can include little graphics in your abstract, so anything that you feel, summarizes, you can pull a graph, from the paper, don't feel like you have to make your own, just kind of like, yeah, this figure summarizes it, and then, do a little summary. So what did they do in the experiment? So just a basic, like, what were they trying to answer? What was their basic setup? And then what was their conclusion? So you just want to cover all that in the abstract. So does that make sense to people? Any questions? And so I'm trying to give it to you. Like I said, I'm already behind, but at least you have it for Thanksgiving. And so maybe you can think about it in Thanksgiving, and then when I see you afterwards in week 10, if you have any questions, we can go over it. But my idea for this is it's not supposed to be like super difficult or punitive, just get you reading the literature and kind of thinking and trying to practice science writing.
Would you want us to turn this in with like physical paper printed out or online?
Either way.
Either way.
Yeah, so I'll accept these. So now I have to go look at the deadline. But basically, I'll probably accept these up until Sunday night before grades are due, so whatever that Monday is. So I think the quarter ends December 8th. And I have to look through my institutional BS. But I think usually grades are due the following Monday. So I would be accepting assignments, probably that's December 10th, it looks like. So get those in. And I'll say 11:59, but so I can wake up early and add your last minute bonus points. All right, any other questions on that? So again, goal is just really get you guys reading the literature and then trying to write scientifically. And I'm not looking to grade people really harshly, right? Just like, did you try it? Did you write something? That's what we're going for to get those bonus points. Questions? All right, so I'll post that after lecture. So now I think we're ready to dive into stoichiometry. And so, right, we were talking about how we can get our composition and all those good things, and that's nice. But now let's get, to the meat of it. So what is this about? What are we doing? And so we have our kind of balanced equation. And so again, right, this is a powerful thing of the balanced equation, is it tells us, what we're reacting. So there's so many things that we're getting from this. We have our reactants, we have our states, right, that tells us at least some clue of how we're going to have to add them together. And we have our products. And then, of course, right, with our balanced equation, we have our ratios. And so our ratios, right, specify the relative amounts, and then they're always in moles, or of course, right, atom to atom, molecule to molecule. But really, in the practical sense, right, we're talking about moles. And I always kind of make a joke, right, moles is your safe space. So, right, anytime you're looking at a question, and that's where people get confused, because they're like trying to give you stuff in grams or maybe volume later we'll see. But really, where's the moles? So we have to be right in moles to do our mole ratio. And so, of course, right, this balanced chemical equation, we're seeing that we have 2 molecules of octane, right, to 25 molecules of oxygen, to 16 molecules of carbon dioxide, to 18 of water. We can scale that to moles, right? So that also means 2 moles to 25 moles to 16 moles to 18 moles. And so just like a recipe, so this is just like your recipe, so we can scale it, right? So times 10 if we want to, whatever, right? It doesn't matter, just as long as they're always in the appropriate ratios. All right, so then we're going to make a food analogy, and then hopefully when we switch to chemicals, people won't forget everything. And so I started off with our balanced equation. And so, right, we can make 2 graham crackers plus 1 jumbo marshmallow, and then 3 chocolate pieces, so that equals 1 s'more. And so now let's start off with this first problem. And so take a few minutes. If you want to make 10 s'mores, how many pieces of chocolate do you need? So what answer do we get?
30 pieces of chocolate.
So 30, and so this is usually pretty easy and intuitive for people to see, but let's do this formally. So again, when we see the moles, we don't get scared. And so, right, if we have 10 s'mores, and so what y'all did, without realizing it or not, is you then compared, right, your mole ratio. So you saw, well, for every 1 s'more, I need 3 pieces of chocolate. And so we can write that as our conversion factor. Again, seems easy right now, but once we throw moles in, I'm sure people will forget. And so exactly, so 30 s'mores. And so, right, if you're doing this with not wonderful chocolates and marshmallows, again, you're just doing your ratio, so however many s'mores to however many reagents. All right, so now try this next one. So if we have 32 graham crackers, how many chocolate pieces do we need here? Take another minute or so. And then chat, I'm watching chat for answers. Do we have an answer for this one?
That's what I'm thinking too.
So I hear some 48s, and so let's just double check that. So 32 graham crackers, and again, right, mole ratio. So I have, for every 2 graham crackers, I need 3 chocolate pieces. So your 48 sounds good, and I'll just plug it into the calculator so we're all on the same page. So 32 times 3 divided by 2, it's 48, just like everyone said. So good. So again, right, just looking at our mole ratio, if we were given moles. And so now let's try a little different problem, right? So they usually don't just give us nice moles. And so let's go back to this problem. So you may need to write this down. So write your molecular weights, right, for these substances. So we have graham cracker. 1 graham cracker is 55 grams per mole. one marshmallow is 76 grams per mole, and one piece of chocolate is 15 grams per mole. So now that we have that information, so if we have 546 grams of marshmallows, how many s'mores can I make if we have excess crackers and chocolate? So take a minute or so to go through that. Do we have answers?
Yes.
I think 7, yeah.
All right, so let's see. So I assume, did we go from grams to moles? And so we said, right, 543 grams, so divided by 76. And let's see,
Equals 7.1447, blah, blah, blah.
equals 7.14 moles of at least marshmallows. And then, of course, last step, they're in a 1-to-1 ratio, and so we can also make 7 s'mores then. Excellent. All right, so now let's do a little bit more involved problem. And so now we have 55, or sorry, I was trying to remember what our graham cracker weighed. So we have 430 grams of graham cracker, 375 grams of marshmallows, and 250 grams of chocolate. What is the limiting reagent? So which one's going to run out first? So this is a type of problem we'll see in chemistry. And often what you're trying to figure out, right, when you're in the lab, what can I make? What's my scale going to be on? And then, of course, how many s'mores? So take a couple of minutes to do that. Try to rewrite the molecular weights for you.
Are the weights per one?
Yeah, for one, so 1 mole. So 1 graham cracker is 55 grams, 1 chocolate's 15. we have answers?
Your graham crackers are your limiting factor, and you can make 3 s'mores. You can almost make 4.
Yeah, that's what I got.
All right, so let me do the work. So you did, so 430, so divided by 55, and then we need to set up our ratio. So then for every, right, 2 graham crackers, make 1 s'more. And you,
3.90, repeating, is an endless stream of 9s and 0s.
so 3.90, excellent. So s'mores for that one. So sounding good, sounds like everyone's getting there. So let's go through the rest. So for marshmallows, we divided by 76, and then they were in a 1-to-1 ratio. So how many s'mores did you get with our 375 grams of marshmallows?
4.8.
So 4.8, sorry, I did that backwards. 1 s'more for every 1 marshmallow. So 4.8 s'mores. Does that sound about right to everyone? Excellent. So I got some nods. And then the last one, so 250 grams, right, divided by our 15. And then except it's 1 s'more, we need 3 chocolates. And so what did y'all get?
5.5 into forever.
5.5 s'mores. So everybody got our graham crackers, then it sounds like. Did anyone have any questions on that one? So we're feeling pretty good. Yeah, question?
If you just know the total weight of like the graham crackers, can you just skip the divided by 2 and just like do the immediate conversion to s'more? Does that make sense? Like you know that if it's gonna be like for 1 s'more there's 110 grams of graham crackers. Like can you just put that under 1 s'more? Or should we do the divided by 2?
So you could totally, what I call it, mass balancing and like doing that. The reason why I don't teach that is just because it tends to confuse people if I go back and forth. So if you see it that way and you feel totally confident, go for it. It tends to confuse people once we like actually start talking about compounds. If you still see it with the compounds, by all means go for it. But yeah, and we can always, talk later about how to mass balance, but if I start talking about mass balancing, yeah, then people will,
I'll get confused.
yeah, everybody will get all confused. So that's why I stick to the moles, but yeah, you're not wrong. All right, so now that we've felt really good about this one, so this is an old quiz that I used to give out in some other class at some other place, and for some reason people would do horribly on it. So now let's see if we can do this. And so this quiz kind of walks you through everything, so let's just start it. And so we'll start with the easy parts with the setup. So we have a balanced chemical equation, and if you haven't gotten my theme yet, I really like this Haber-Bosch process. So of course it has a lot of relevance, right, to making ammonia. A lot of energy is involved in that, and then a lot of research goes into trying to make catalysts that would do this at ambient temperatures, like the nitrogenase. And so now let's just calculate these molecular weights. So take a minute or two to do that. So what do we get for the molecular weight of H2? 2.016. I like it. Nitrogen,
N2 is 28, about.
it's about 28 grams per mole. And then ammonia, 17.031 grams per mole. All right, so now let's try the first problem. And so I'd probably write down this equation if you haven't already. So 1 nitrogen plus 3 hydrogen gives us 2 ammonia. So then if we have 4 moles of hydrogen, how many moles of nitrogen do we need to fully react? Do we have an answer? Ooh.
12 moles of,
Ooh.
I think it's 12 moles of nitrogen.
One mole of N2, because at least in the question it says H2 and N2. Are we doing nitrogen or just diatomic nitrogen?
So it's asking for N2, but it doesn't matter. But I still disagree with all those answers.
That would be 1 mole and a third mole?
Yeah, so 1 1/3, right? So set up your mole ratio, and that's why I say don't let the numbers confuse you. So right, 4 moles of H2, it's asking for N2. And then right, look at your equation, and that's what I mean. So the s'mores numbers feel easy, but sometimes with these weird numbers. So your setup should look something like this. So we're solving for N2.
So it would be 1.3 moles.
Yeah, so 1.3 or 1 1/3 moles of nitrogen.
Trying to solve a little risk is like you want to cancel out whatever's at the bottom and you're trying to find whatever
Yeah,
is on top.
exactly, right? Use your dimensional analysis.
It's easy to flip it around and say, oh, 3/1. But if you're trying to find the moles of nitrogen, you just put the hydrogen at the bottom and the other side hydrogen on top.
Yeah. All right, try this next one. So if we have 2 moles of nitrogen, how many moles of ammonia will we produce? Do we have an answer for this one?
4 moles.
So 4 moles. Is that what other people got? And so that looks good. So we set up our ratio. So for every 2 moles of N2, and then we go back, right, for every 1 mole of nitrogen, we need 2 of ammonia. So exactly, so 4 moles. Questions on that one? Yeah.
I guess, if I get it correctly, you, the first parentheses, it's what you're supposed to, or the information we have at times of its ratio of the product in the equation.
Yeah, so it's just write your mole ratio.
Okay.
So just whatever you're interested in. So in this case, it was a product, right? But before we were comparing like reactant to reactants. So yeah, it's just whatever you're comparing. All right, so now let's try a little trickier one. So 6, 7, and 8 are related. And so it asks us, if we have 20 grams of nitrogen, how many moles of hydrogen do you need to fully react? If you have 20 grams of hydrogen, how many moles of nitrogen do you need to fully react? And then which one is the limiting reagent? So maybe let's start with 6, I guess. We'll do this kind of step by step. And we'll check in with everybody. So take a minute or so to do 6. I'll rewrite our equation. Do we have answers for 6, or we still need some time?
I got 60 grams of, or 16, oh, it's a lot. It is asking for moles.
I got 2.14, yeah, 2.14.
So walk me through. So we started with 20 grams of nitrogen, and then what did you do from there?
And then we divided by the mass that we have to get the moles that we have. So the 1 mole for, in our case, 28.14 grams.
28.14 grams.
Or
Excellent.
0.14.
Oh, 0.14, sorry.
And that would equal the amount of moles that we have available, which is 0.714. And then we multiply it by the ratio of hydrogen, diatomic hydrogen to diatomic nitrogen, which is 3 diatomic hydrogen per 1 diatomic nitrogen. And in fact, it's
Oops, my bad. So 1 nitrogen.
I believe it'd be,
Would it be multiplied
yeah, it'd be the
by hydrogen?
3
So
hydrogen
the
over 1 nitrogen.
hydrogen would be on top?
Oh, my bad, sorry. Apologize. All right, so does that look like what everybody did? So 20 divided by 28, and then times 3. Oops. Oh my gosh. Sorry, calculator misfunction. So you said 2.14, right? Excellent. So 2.14 moles of H2. Questions about 6 here? So now try 7. It's now 20 grams of hydrogen. And how many moles of N2 do we need? Do we have answers for 7? So walk us through. Larry, you want to go for it? You're volunteering again.
And we have, again, 20 grams, except this time of hydrogen, or diatomic hydrogen. We can, of course, multiply it by a ratio of 1 mole per, I believe it was 2.016 grams of hydrogen. And then, I guess, rather than completing through this calculation, we can just go straight to the next conversion, which would be 1 diatomic nitrogen per 3 diatomic hydrogen. This would give us the final answer of 3.306 7 moles of nitrogen react.
So about 3.3 moles of nitrogen. So is that what everybody got? Any questions on that process? And so now looking at these, and so I know you skipped over this calculation, so you might want to do this. So how many moles of hydrogen did you end up?
9.9206.
9.920 moles of H2. So now looking at all this information, right, which one is a limiting reagent? So take a minute or so to think about it, kind of what we calculated. So what are we thinking based off of this information?
It seems like the hydrogen would go up first.
So take another look, because
Well, the only other answer would be nitrogen, so is that the right answer?
it is, but why? Now you guys got to explain it to me.
What I did was I took the 20 grams of N2 and converted it to moles and gave the whole multiply by 1 mole over the grams per mole. And then I multiplied that by the ratio of diatomic nitrogen to ammonia.
So you basically, so let's maybe do that.
And I did that for each one and just saw that the moles were a lot smaller for nitrogen.
Yeah. So there's different ways to look at it, right? So you could kind of look at the moles, and that's what I was kind of getting at, is with the nitrogen, right, we only have 0.714 moles, but we said, well, we needed 3. So, right, we have a little less to react, right? So that doesn't really work out. And so same thing if you do it in reverse, though. So with the nitrogen, so the nitrogen only requires 2.14 moles of hydrogen, and we had 9 there, right? So that one's the excess. But if that wasn't clear, then yeah, going back and then recalculating it for each one. So I'll just kind of start here, right? So we had 0.714 moles of nitrogen, and then going back, right, doing the ratio, so 1 nitrogen gives me 2 ammonia. So that's what, like 1.4 moles roughly. And then, so doing for hydrogen, so if it was about 9.920 moles, and then it's a 3 to 2, hydrogen to ammonia. And so let's see, what do we get? 9.92 times 2 divided by 3, and so that was 6. So 6.13. So either way, so kind of the point of that is, right, try to see multiple ways to get to that answer. What are we saying, right? Because, you know, we calculated it all out, how many moles we need of each one, and then comparing, right, how many we had, or just comparing how much product. All right, so with that information, so we landed on nitrogen being our limiting reagent, and so now see if you can figure out how many grams of ammonia would be produced. We're basically there. And do we get an answer for this one? So what do we get for grams of ammonia?
I got about 24.4.
So 24.4, so did you take this 1.4 roughly?
Yeah, I use three significant figures, so I just did 1.43 and multiplied it by the atomic weight, which is 17.031. The atomic weight of the ammonia.
So that sounds good. And you said you got 24, right? Or roughly?
Yeah, about 24.
Plug it in. So 24 grams about. So did everyone get that? So excellent. And then the last type of problem that we'll kind of see in these things is our percent yield. And so, right, this is considered our theoretical yield, right, what we expect. So 100% yield, everything goes perfectly. And of course, right, we know in lab, usually that doesn't happen. You know, you drop half of it or whatever, or bad reaction. And so let me give you the formula, even though I think we've done it in lab, but right, so percent yield is then just your actual over your theoretical, and then times 100 to make it a percentage. And so what do we get for this percent yield here? So 17%. And so it sounds like somebody messed up this reaction, you know, who knows what happened, but yeah, leaky valve, who knows? And just for context, so like an organometallic reaction where you add like a metal plus a ligand, those tend to be like 50% yields, and then like organic chemists, especially like total synthesis, they try to aim for like 90% or higher. And obviously, right, if so like a synthetic organic chemist, they could be doing like natural product synthesis that could involve, you know, 20, 30 steps. So they really want to get, you know, 90% and higher in each step, since of course, right, your total yield. And so I think we've seen this before, but let's just say, you know, assume a 20-step synthesis, and right, and this would be optimistic, so 90% yield on each step. And then, right, you take that 0.9, take it to the power of 20, right, because that's your overall yield for these poor synthetic natural product chemists. And so, right, that gives you an overall yield of 12% by the time you're at the last step. So that is kind of depressing. But yeah.
Is that like about what it usually is?
Oh yeah, I've heard plenty of horror stories of, like, you know, natural product synthesis chemists, if something wrong happens in your last step. So horror stories I've heard are, so there's a thing called a rotovap, where it basically just evaporates off solvent. So I'll show you a picture. So it looks like this, but right, this little bulb thing, it can contain your product. And so I've heard horror stories where it's popped off, goes into the water bath, and you know, that's like your last step. So the poor chemist is doing an extraction from the water bath. I've also heard, I don't know how this happened, but like something went down the drain or something, and somebody was trying to do like a drain extraction. People get desperate if they accidentally lose their product on, you know, step 20 or whatever of a total synthesis. But I don't encourage the total synthesis life. But that's a different level of dedication and pain that those chemists do. All right, so blah, blah, blah. So this is just our formula for our theoretical yield. So that's there. And actually, we're pretty much on quiz time, it looks like. So I guess we'll end there. So if we need more practice, we can do more practice with stoichiometry kind of next week, depending how we're feeling. I have to remind myself what's on the agenda. But otherwise, we can take our 10-minute break unless people want to. Should I just hand out the quiz? All right, I think I'll just hand it out. If you need to take a break, you know, obviously go take a break. But I know people are trying to get places. Get started. If you want to get started, obviously take a break.
And the testing says it goes across the way like that.
Yeah, so right next to it.
Hydrogen peroxide breaks up the hemoglobin, which gives blood its color, so the color.
Are there any questions online? I'm probably going to stop the stream. And then if people want their quizzes emailed, just let me know and I will send them.